to work on some of the concepts that Sergio gave in the prior talk and try to think about some of these ideas from the point of view of garbled circuits, which is one of the tools that Sergio mentioned, and how this garbled circuit tool relates to the rest of the tools that are available. I'm going to focus and tell a little bit of how garbled circuits is constructed, but I'm trying to organize or place a garbled circuit with respect to the rest of the available things that are there to help us solve the problems that we want to solve. So I'm going to revisit quickly some of the things that Sergio said using my own words. So why more computing? Again, because we want to do more things. There are a lot of interesting things that could be done. Sergio mentioned the obvious thing is bridging. We want to build bridges. It's everybody wants to be bridges. Want to use bridges in particular to create L2s and to connect Bitcoins, the actual money, with these L2s. But there are a lot of additional really interesting applications that makes a lot of sense. And when the dust of building bridges set, we will see a lot of other interesting applications behind that. And we need to think about all those applications. As Sergio mentioned, the problem is that in order to build those applications, we need to be able to execute a lot of computing, and it's not practical to do that directly over Bitcoin. It's really not practical in other chains also, because even though Ethereum and some of the other chains has more expressive smart contract languages, we want to do a lot of computation in order to create sophisticated protocols, and it's not enough what is available neither on Bitcoin with the scripting language that we have here. And Sergio mentioned also it's about the amount of computing you want to do, but it's also about connecting different transactions, because some of these protocols, of course, they are interactive. They mean interaction between different parties, and that means different transactions, and you need to carry data from one transaction to other transactions, and that's not easy with the tools that are available today. So we need more computation. We also need to publish data related to these applications. We need to select things or let the players, the different agents, show what they're or register what they're intending to do. And sometimes that could be also costly. As Sergio mentioned, in Bitcoin, sometimes it's not obvious the difference between data and computing, because every instruction, it's just 1 byte in a sense. So it looks like the same, but conceptually, when you're designing the protocols, it's a different thing. And as I mentioned, how to connect different transactions. So the solution is to try to move as much computing as possible out of Bitcoin and into the off-chain world, wherever that is, and to keep as small as possible to keep things secure on Bitcoin. We already saw all of this. I have this here for completeness, let's say. So in order to achieve this idea of moving things out of Bitcoin or of other chains, we have several tools available. Sergio spoke a lot about disputable computation. BitVMX, it's an implementation of disputable computation or dispute resolution protocol, as well as other protocols integrated with it. The idea is to try to claim a result of the computation on chain and have some way to resolve potential wrongdoing from the one who is claiming the result. We spoke a little bit about this idea of having log n. This binary search has log n interactions, and then you only need log n interactions and one execution of one single step of the computation in order to validate it on chain. So this allows us, in principle, to do a lot of computing on chain by moving all that computing off chain and claiming the result during the binary search. We have, of course, CK proofs. Sergio also spoke about that. There's been a lot of interest in CK proof, a lot of startups in the past decade related to how to use CK snarks, starks, and other systems in order to create some interesting applications. The main use case is rollups. The main use case that comes to mind is rollups, because you can use the succinctness, the S in snarks and starks to exhibit the result of a computation in a much more reduced way than the original computation. How this verification scales with the original, with respect to the original computation is important, and there are different trade-offs. But in general, what we use is this idea of using some very expressive, very good proving system that lets you create recursive proofs and do very long computing, and then wrap it into a Groth16 proof system that has some interesting benefits. In particular, the proof size is always the same size, just a few group elements, and the verification is always the same cost, which is what I'm mentioning here with O1. The time required to do the verification is fixed. But we're usually thinking about this idea of succinctness from the point of view of what can be gained in terms of reduced computation. But it's a really interesting benefit, which is the fact that a lot of auxiliary data, additional data that the process needs in order to make its computation, we don't need to publish that data, and the fact that we are hiding that data inside the CK part, the CK witness of a proof, is really valuable for many of these protocols. Why? Because if we want to do disputable computing directly and do this binary search, for example, to validate the blockchain state, and we need to kind of rewind and recompute all of the transitions from the blockchain, that computation will need to have, although this is public information, we need to have available this information, the information about the different blocks of the history of this blockchain. So we will need to provide that information to the computing process. Doing that on chain, we'll need to publish or have some way to signal what is that information. On the CK proof side, that is not really necessary on many applications, because we can basically put that as part of the secret witness. I think that there is a succinctness of requiring information for the execution of the application of the verification function, which is really interesting that we get this out of CK proofs. And that's why even though maybe this log n execution is really give us the possibility of running longer, I don't know, 1 billion instructions in just a few tens of steps in the binary search. Even in that case, we will still want to use probably a CK proof in order to reduce the amount of information that is needed. The other element that's taking a lot of attention lately is Garbled Circuit. Garbled Circuit is one solution to the problem of secure multi-party computation. Secure multi-party computation. For a couple of years, whenever I mentioned secure multi-party computation, I got everybody understood that I meant threshold signatures, because that's what everybody was using MPC for, like to create. But MPC is much more than that. It's one of the oldest protocols or cryptographic primitives available. And Garbled Circuit, it's one way to create a solution to this problem, to the problem of functions with a potential adversary, I would say. And garbled circuits, what has in its favor, and I will talk a little bit about that just in a few seconds, it's the fact that you do most of the interaction during the setup phase, and then the rest of the protocol, you don't need almost no interaction among the two parties, and that is really good for the liveness of these protocols. That's why we're using garbled circuits and not some of the other MPC protocols, which can be more efficient, but they have this liveness requirement that is complicates things. Besides the tools that I mentioned, there are other elements around that could help and will be probably useful in the near future. We have fully homomorphic encryption and somewhat homomorphic encryption. In a sense, MPC has something about homomorphic encryption working on it. The protocols are not efficient enough to be practically useful yet. Meanwhile, garbled circuits is helping solve those problems in that way. There are potential applications of private information retrieval that could help implement some protocols. We have some discussions about that. It's not that common recently, but we will anticipate there is going to be some use of these kind of tools in the near future. And there's always discussion about witness encryption. Witness encryption, which is the possibility of creating some encrypted data which can only be accessed given some conditions, can be decrypted only under those specific conditions, which is in a sense what we are trying to emulate on different scenarios. That this could help solve this problem, but it looks like many of the problems that we want to address, but it looks like it's not going to be that easy to have a general solution to the witness encryption problem. So this is the battery of things available when we are trying to attack some of the problems that we were describing in order to get more sophisticated protocols working in a practical sense. We go on, this is what's on our toolbox, and I'm going to focus a little bit on garbled circuit as I mentioned, because it's the one that is going to be giving us a lot of value in the short term. So what I'm going to do is talk a little bit, give a kind of low-level description of how MPC and garbled circuit works. As I mentioned before, the original MPC problem is the problem of having a functional evaluation among different parties, provided those agents don't completely trust each other. That is what we want to solve. It can be seen also as trying to, if you don't trust each other, then they don't want to give any additional information than the information that we need to provide in order to execute. So maybe learn the result of the functional evaluation, but keep their inputs hidden. That is the original setting for MPC. There are some other settings that are also related to MPC, which is the privacy-free setting, which is the one where even though both parties they know what are the inputs of the circuit and they know a lot about the intermediate states of the circuit, they want to validate a particular output and to have this signed output out of the circuit, and that is also a valid use case. Besides that, the idea is to try to use garbled circuits to make sure that the result of evaluating this function is correct, and that no party can cheat and claim that the result was different than the one expected. That is the basic use case that we are going to be using with garbled circuit. How do we construct garbled circuits? Basically, the first thing that we're going to do is we are going to assign labels to each wire. We have this binary circuit where each wire has a binary value. When it's going to be evaluated, we're going to be assigning either 0 or 1 to each of the wires and then do some calculations. And the garbled version is an encrypted version that is going to have, instead of a 0 or 1, it's going to have 2 random labels that are going to be used to represent 0 or 1 on each of the wires. This is true for the inputs, for all of the intermediate wires, and also for the output wires of the circuit. And what we are going to be doing is we're going to be constructing for each gate a kind of truth table that describes what are the outputs for this gate that are expected given all of the possible combinations of their inputs. So in order to be able to evaluate the gate, we are going to be trying to evaluate these gates in an encrypted fashion. So we will try to get input to these gates as encrypted labels. I will want to compute the result of the gate in an encrypted way too. And in order to do that, we have 2 roles here. One is going to create the circuit, that's the garbler, and one is going to evaluate the circuit. The garbler is going to create for each gate 4 values for ciphertext, which are the encryption of the output of the gate for each of the 4 combinations of inputs. And what's going to be doing is encrypting the output using the labels of the input as a key. For example, if I enter the AND gate with a 0 and a 0, the left side is 0 and the right side is 0, I have not the 0 itself, but a label, a random value that represents a 0. So what I'm going to do is I'm going to choose the 2 output values, 2 labels for the output. I'm going to encrypt the 0 output using X0 and Y0 as key. Then I'm going to encrypt the 0 output again using X0 and Y1. This is, if I enter with 0 and a 1, the output should be a 0. So the evaluator can use this to decrypt this. So I'm going to be providing this in encrypted fashion. For this other combination, X1 and Y0, I also get a C0. And the AND gate only gives a 1 in its output if we have X1, Y1. The interesting aspect of this scheme is that I start with some encrypted wires. I do the calculation using these tables that were provided, and I get an encrypted wire at the output. And now these encrypted wires, they can again be used to evaluate further gates. So these gates can be composed, and a secret can emerge out of these small computation of individual gates. So in the end, I place these inputs. I have these tables, and I can evaluate the whole circuit and have assigned encrypted labels for each wire. Okay, so the idea is to use now this huge circuit as a black box, in a sense that can be used to evaluate a complex predicate that will say what is the result, or if the result of the computation, or to say that, for example, if under these conditions the operator can withdraw and take the funds and transfer the UTXO. And what's going to be happening in this case is that Alice is going to be generating this circuit and all of the encryption labels, and all the labels and all the encryption tables, and give this information to Bob during setup. Alice is also going to be telling Bob what is the hash of one of the 2 output labels, the output label for a 0. And Alice is going to give all of this to Bob, and then afterwards, during the usage of the circuit, at some point, Alice is going to be publishing the labels for each of the inputs. Bob can evaluate the whole circuit by processing each gate using the encryption tables, and obtain either output 0 or output 1, one of the 2 labels for for the result of the circuit. In the case of the circuit giving the false result, that will mean that Alice was not allowed to withdraw the funds, and Bob will be able to obtain output 0, the secret label that is going to be used to stop Alice from taking the funds. If the inputs were correct, in that case, Alice will obtain output 1, but output 1 is useless for Bob. Output 1 is useless for Bob. Bob will not be able to stop Alice from taking the funds. And after a timeout period that is there to let Bob challenge, Alice will be able to claim the funds and take them. This is what is called a conditional reveal of a secret. The idea is that the circuit can implement a complex logic that will decide whether the inputs were correct. And if the inputs were correct, the secret remains hidden. If the inputs were incorrect, then a secret value is revealed, and that secret value can be used to connect to some other transactions in order to affect the execution of the protocol on Bitcoin. There is one more problem that we have not resolved yet, is the fact that Alice generates the circuit and provides some encryption tables for Bob for Bob to later use in decrypting and evaluating the circuit, but Bob doesn't know for sure that these tables were really encryption tables for the proper circuit or were just random stuff. And if this circuit is not properly represented on the encryption tables, then Bob will not be able to recover the secret. As a matter of fact, Bob needs to know that hash of output 0, should say here, hash of output 0 is a correct hash of the output label that's going to be revealed on the correct case. There is one solution to this problem, which is to basically generate a few number of circuits, and Alice generates not just a single circuit, but generates I don't know, 40 circuits. Bob asks Alice to reveal 20 of these 40 circuits, and the idea is that if Alice was planning to give wrongly generated circuits, Bob will, with high probability, identify one of these wrongly generated circuits on Alice, on one of the ones that choose to open, basically. That is more or less the general idea with what's called cat and choose, which reminds us of card games. And there's also a possibility of using directly CK proof schemes to demonstrate that the encryption tables were properly generated. There are different trade-offs between the different these two approaches. Maybe it's too much detail for today. The idea then is that we are using all these tools to move part of a computation from on-chain off-chain, right? We're using garbled circuit, CK proofs, and all of the other systems. And here, what we need to analyze is exactly what are the new costs associated with the execution of these protocols. And the new costs are not protocol fees, because we are reducing protocol fees, but we have, in exchange of that, we are having some computing costs, because generating some of these circuits and doing some of this encryption can be expensive. Of course, depends on the size of what you're trying to do, but this is something that starts to be significant. There is some communication and storage costs, because as Sergio mentioned before, if we are going to be sharing these encryption tables, we will need to store them, so they're going to be available at the time of needing it. When Alice decides to execute some operation, I will need to be able to get hold of that table, so we need to store that, and there are storage costs. Storing information is getting cheaper and cheaper. It's more slow. There's a lot of reductions in cost associated with storing data that we can anticipate. But as of today, it has to be considered. We need to do the math and calculate exactly how much information we need to store in order to run these protocols. So just to wrap up this first part, that makes a lot of sense to move things off chain. There are many trade-offs, many parameters that need to be considered, and choosing the right setup it's really important and part of the engineering challenge that we are facing at this point. And as Sergio mentioned, there is a lot of activity. What in this particular field, most of what we are discussing is really, really new, or are new ways to use old things, but most of our current understanding of how to solve these problems is really, really new. And if you ask us last year what was the best way to solve these problems, the answer will probably have been a different one as of today. And we're anticipating that we will see different solutions in the near future because there is a lot of activity here. That's it. Thank you. We are going to be. Should we do some questions, or maybe we can do a pause? Yeah, let's. We're having a coffee break now, and thank you, guys.
10 minutes.